Let's get into the ocean now. Ocean typically is characterized by the nonlinearity of its density in terms of a function of temperature and salinity. You're used to fresh water where obviously warm water will have a lower density. Adding salinity increases density of the water, as you can imagine. So this TS diagrams are very typical of oceanography, especially those who go on ships and measure properties, and they can taste the water and tell you where it comes from. Maybe Arnold Gordon will tell you that he can. So here is a range of temperature going from -5 to 35. Hardly ever it gets to -5 because even with salinity, the freezing temperature tends to be about -2 or so, I think. Nonetheless, looking at a broad range of salinity going from 30 to 40, it can get much fresher in many places where the rivers are coming into the ocean. And you can see that the density lines, constant density lines, are not linear functions of TNS, and of course as temperature increases at constant salinity, density decreases, and if you take a constant temperature and increase salinity, then density increases. So why are these numbers given as 30.9 and 27.9 and so on? The density of pure water is 1,000 kilograms per meter cube, and the density of ocean water, when you add salinity, is going to be slightly above it. So the density is typically expressed as sigma, where you take out the 1,000 and just leave what is above 1,000. So that's what is being shown here. And these arrows show you that at a colder temperature, the same change in salinity is going to require a larger change in temperature to accomplish a similar change in density. So the density is a nonlinear function of temperature and salinity. So at a warmer temperature, the change in salinity and temperature needed to accomplish the same change in density is going to be very different, right? So small warming here is going to give you a change in density for the same salinity, whereas here you're going to need a larger change in temperature. Okay, I think you know what the point. But the other point you can see is that if you take two water masses on the same density line and mix them together, so let's say you take A and B and mix them, X here will have the average salinity of these two and the average temperature, which is going to give you a density that is not on the same line anymore. Okay, this magic happens because of this nonlinearity, and it's called cabling, where you take the same density with different combinations of temperature and salinity. When you mix them, the temperature is going to become the average of the two, the salinity is going to become the average of the two. It's just a linear mixing process, and that's going to result in a density that's new, even though they started with the same density when they were mixed. This is called cabling, and it can be important in some regions of the world where you have a lot of freshwater forcing or a lot of glacier melt and so on and so forth. Looking more specifically at the ocean sections, this is an equatorial section here, and this is at 60 north and this is at 30 north. We'll come back to this in a more simplistic diagrams where we can look at the vertical profiles. I have podcasts on thermocline, vertical structure and so on that you can look up, but you may be already aware of the concept. Near the surface you are going to have warm temperatures and fresh salinities in the equatorial region compared to 30 north, which is in the middle of the subtropical gyre, which is a net evaporative region. And at 60 north, temperatures are going to be drastically colder, and the salinity depends on whether you are in the North Atlantic at 60 north or in the North Pacific at 60 north, because they are dramatically different salinities. Because in the ocean, salinity at the surface is determined primarily by exchanges of evaporation and precipitation. other than places where, as I said, river and glacier melts may be coming in. Okay, keep those in mind because ocean also has a circulation similar to the atmosphere that we will look at. Considering this temperature and salinity dependence of density, there is a thermal expansion coefficient which determines the density change with temperature at constant salinity, and there is a salinity impact on density at constant temperature. It turns out that the thermal expansion coefficient is quite sensitive to temperature, so it can vary by a factor of 4 in magnitude when you go from a temperature of 2.5 degrees to 30 degrees centigrade. So it goes from 781 per Kelvin here, because you are dividing by density, so it's only the temperature, to 13 times 10 to the minus 7. So that explains part of the nonlinearity in the water properties as well. Whereas the salinity contraction coefficient is not that sensitive to water mass changes. Okay, so varies a little bit, but not that much. There is also a pressure effect on these two that is important when you go from the surface to the deep ocean. These are kind of scientific curiosities that I won't go too much into. Basically, the book looks at the volume percentage occupied by the various combinations of salinities and temperatures and the surface area. The main story there is that if you look at the warm temperatures and the salinity ranges, why do we look at warm temperatures? Because this determines the interaction of the atmosphere and the ocean. Where temperatures are warm, we will see soon that atmosphere tends to respond very strongly because of evaporation, rising air, expansion, convergence of air masses to fill the rising air for mass continuity, precipitation, convection, and so on. And the main story here is that the warm temperature water occupies a large area of the world ocean, just in terms of, I don't know why this computer does this, but it has a very small volume, which means that it's a very thin skin surface on of the ocean. Much of the deep ocean is cold, and it's not directly going to see the atmosphere on fast time scales. So we'll see that ocean has a fast and slow time scale. Atmosphere also has a slow and fast time scale. The structure looks like this. Equator is warmer, so the pycnocline and the thermocline, constant density interface, and the constant sharp gradient in density and temperature are shallower. They are deeper where the convergence and sinking of the water happens in the subtropical gyres, and at high latitudes surface cooling creates these layers that are going from the surface to the deep ocean. So how the water sinks, how the atmospheric properties get taken down, how long the water stays down there versus in these regions, and so on, are all going to depend on this broad structure. So as I mentioned before, in the atmosphere it's very common to look at zonal mean meridional sections, but in the ocean that doesn't always make sense because we have strong boundaries. Let me add a little bit. The vertical structure typically looks like this. Near the surface you have constant wind mixing and either cooling or heating of the surface because of heat exchanges and evaporation and precipitation. So there is turbulence created, which creates vertically mixed constant temperature and salinity or constant density layers. Before that you have this sharp gradient in temperature and density, which we call thermocline or pycnocline, depending on whether it's temperature or density. And then as you go to the deeper ocean, the temperature and the salinity and density become almost the same. So if you look at different sections from the tropics to mid-latitudes to high latitudes, the difference becomes obvious that as you go to deep ocean, whether you are in the tropics or mid latitudes or high latitudes, you're going to get similar temperatures and salinities and densities. So these processes are very critical for the heat and water exchange or hydrological exchanges which we are talking about in this chapter. So we'll come to the details of those processes, especially in the context of a monsoon, El Nino, interseasonal oscillations like Madden-Julian oscillation, and so on. Okay. Ocean also has the other circulation where there are regions with very high density water being formed at the surface that sink like a rock to the bottom. They flow and occupy rest of the world ocean on very long time scales, hundreds to thousands of years. That water is slowly converted back to the surface water and flows back in these lighter gray arrows to the regions where the water sinks. So the Greenland, Iceland, Norwegian Sea and the Labrador Sea and the Ross Weddell Seas in the Southern Ocean are all formations of deep and intermediate waters with various density contrasts, heavy enough to sink. They are mixed in this mixing bowl of the Southern Ocean, and then they are pumped into the Indian and Pacific Oceans, where they slowly get converted to surface water and flow back through the Indonesian seas here, south of Africa, back into the North Atlantic. Okay. Maybe I'll just add this as well. This is something that was discovered in the Toga core. There is some evidence before as well from Stuart Godfrey, I think. We talked about the well-mixed surface layer, so you can see the salinities and temperature are mixed down to this depth, and there is the density. And then density increases, salinity increases, temperature decreases. But there are special regions like the West Pacific where there is a lot of rain, where the temperature is mixed differently than the salt. What does that do? That gives you a different level of density mixed layer versus temperature mixed layer. Why is this important? Because when turbulence entrains this colder water into the surface, it tends to cool the sea surface temperatures, whereas in these layers, entrainment, for example, the mixed layer is somewhere here, and entrainment is going to mix water that's not that much colder, so the surface is not going to cool much even though energy has been used to mix these waters into the surface. So this layer is called a barrier layer because it's a barrier to surface cooling by the entrainment process. This becomes critical in many places to determine how sea surface temperature responds to the turbulence and mixing action by the winds or cooling and heating action by the heat exchanges. So these are processes that are important, and we will remember them, but we will come back to them again, so don't panic. Few concepts introduced there, all important, but just listen again, read the book, make sure you understood it.